Hey everyone! So if you're taking calculus, you know exactly what I'm talking about. Spending what feels like forever working through the formal definition of a derivative. It's a lot. But what if I told you there's a way, a much faster way to do it? Well, today, we are unlocking the shortcuts that are going to completely change the game for you when it comes to differentiation.
Oh yeah, I can practically feel you nodding along right now. We have all been there, right? Setting up that limit as h approaches 0, expanding all those polynomials, hoping everything cancels out just right. It is an absolute grind. I mean, it's super important for understanding the concept, for sure, but for actually solving problems, it's just not efficient. It's kind of like having to build a car from scratch every single time you just want to go for a drive.
And that is the good news, because there is a much faster way. We're talking about a whole set of powerful formulas, shortcuts really, that mathematicians and engineers use every single day to get this stuff done in a fraction of the time. So, get ready, you're about to learn how to drive that car, not just build it.
All right, let's get into it. We're about to build our brand new toolkit, and it's all based on 3 super fundamental formulas. Seriously, if you master these, you'll be able to differentiate pretty much any function that gets thrown at you in intro calc. Okay, first up, we have the undisputed champion of differentiation, the power rule. It's just so simple and so powerful. All you do is you take the exponent, bring it down to the front to multiply, and then you just subtract 1 from the original exponent. That's it. And here's the really crucial part. This works for any real number exponent. I'm talking integers, negative numbers, and yep, even fractions. This rule is about to become your new best friend, I promise. Next up, we've got the constant rule. And this one is, well, it's just super intuitive when you think about it. Remember, the derivative is all about the rate of change. It's the slope, right? So if you have a constant function, like y equals 5, what does that look like? It's just a flat, horizontal line. And what's the slope of a horizontal line? 0. Exactly. So it just makes sense that the derivative of any constant is always going to be 0. So simple, but so important.
And finally, we have the rule that really lets us tackle those big, sometimes messy-looking polynomials, the sum/difference rule. Now, this rule tells us that differentiation is linear, which, is just a fancy way of saying you can tackle a big function piece by piece. You just break it down into its individual terms, find the derivative of each one separately, and then you just put them all back together with the plus or minus signs. This is the rule that makes the whole thing manageable instead of a total nightmare. Okay, so theory is great and all, but let's actually put these rules to work. We're going to take a pretty standard polynomial and just see how incredibly fast we can find its derivative with our new toolkit. Let's do this.
So here's our example problem. Y equals 5x to the 7th minus 3x squared plus 10. Now, just imagine for a second trying to do this with the old limit definition. It would be a ton of work. But with our new rules, watch how easy this is. Okay, so thanks to that sum difference rule, we're just going to go term by term. Let's start with the first one, 5x to the 7th. We use the power rule. We bring that 7 down in front, multiply it by the 5. That's 35. Then we subtract 1 from the exponent, so 7 becomes 6. Boom! 35x to the 6th. Easy. Next term, negative 3x squared. Same deal. Bring the 2 down, multiply by negative 3. That's negative 6. The exponent 2 becomes a 1, so we get negative 6x. And that last term, the 10, well, what's that? It's just a constant, so the constant rule kicks in, and its derivative is simply 0. And now all we have to do is put the pieces together. The derivative, y prime, is just 35x to the 6 minus 6x. And we're done. Seriously, look at that. What would have taken ages and pages of algebra with the limit definition, we just did in what, 15 seconds? That right there, that is the power of these formulas. Okay, so polynomials are no problem now. But what about those trickier-looking functions? The ones with fractions and roots in them. They can look kind of scary at first, but it turns out the power rule can handle them too. You just need one crucial little trick up your sleeve. This is a big one, because it's where a lot of people get stuck.
And here is the secret. It's so simple. Rewrite it first. Always. Before you even think about differentiating, your #1 goal is to get every single term into that nice, clean x to the power of n format. If you can do that, the power rule will work every time. Seriously, do not try to differentiate a fraction or a root as it is. Rewrite it first. That's the key.
Okay, let's look at an example. Let's say we have f of x equals 4 over x cubed. See, right now, we can't use the power rule directly. So what do?
We rewrite it. We're going to use our good old rules of exponents to bring that x cubed up from the denominator. And when we move something from the bottom to the top, what happens to the exponent? It becomes negative. So 4 over x cubed is the exact same thing as 4 times x to the power of negative 3. And look at that. Now it's ready for the power rule.
And from here, it's just business as usual. The power rule works exactly the same way. We bring the negative 3 down, multiply it by the 4, that gives us negative 12. Then we subtract 1 from the exponent. Now, be careful here. This is a classic trip-up. Negative 3 minus 1 is negative 4. So we get negative 12x to the negative 4, which we can clean up and rewrite as negative 12 over x to the 4th.
So what about roots? Same exact idea. Roots are just powers in disguise. So if you see something like the cube root of x squared, you just got to rewrite it. And the rule is simple. The power goes on top of the fraction and the root goes on the bottom. So the cube root of x squared is really just x to the power of 2 over 3. And just like that, we've taken another one of those tricky functions and made it ready for our good friend, the power rule. So let's apply the rule. We bring the exponent, 2/3, down to the front. Then we subtract 1 from the exponent. So 2/3 minus 1, that's negative 1/3. That gives us a derivative of 2/3 times x to the negative 1/3. And if we want to, we can rewrite that back into a radical form, which you see here. The system just works every single time. All right, you've seen the rules, you've seen them in action. You now have the fundamental toolkit for differentiation. But, the only way to really make these skills stick, to make them second nature, is to practice. So, what happens next? That's all up to you.
And look, the absolute best way to get this stuff locked in is by doing problems. Using tools like AI-powered quizzes is awesome because you get instant feedback and you can actually track your progress as you get better and better with these new techniques. So, I'm going to leave you with this thought. Think about those problems in your textbook, the ones that looked totally intimidating yesterday. Well, guess what? They're not so scary anymore. You now have the power to break them down and solve them with confidence. So my question to you is, what complex function are you going to conquer first?